For invitation to give a talk. This well, I will follow probably our chairperson attitude. I will present an introduction of the subject, and then on the last 5 minutes I will discuss about the Braided majorana qubits. The idea of Braided majorana qubits is in relation which is the simplest setting to implement Kitaev proposal of realizing topological quantum computation. The simplest setting is should be Majorana fermions, and the simplest Majorana fermions is a Majorana qubit. And when you have several Majorana qubits, you can braid it in some way. And that's the main idea. But in order, before doing that, I want just to present the context. And the context is the following. We have, of course, when we say about topological quantum computation like Kitaev, we think that we have some application of the braid group, because these offer the possibility to realize knots and links, which offer the topological protection. And braid groups, of course, only exist for particle which lives into space dimension. But before that, there exists another type of parastatistics, which is the parastatistics which is based on the permutation group, not on the braid group. And anyons, of course, have been related with the fractional quantum Hall effect and have also been observed in nature. So they have been experimentally determined. There exist some questions concerning the parastatistics based on the permutation group. And now, first, I want to clarify this context, because then it will be used to go further to the next topic of the braided Majorana qubits. Concerning parastatistics, there is they were being introduced in 1953 by Green by using the so-called trilinear relations for either parafermions or parabosons. And then later, Greenberg and Messier, they introduced a trilinear relation mixing both parabosons and parafermions. This is the starting point of parastatistics in physics. There was a very nice contribution in the end of 70s, beginning of 80s by Bulgarian mathematical physicist Palev, that proved that the trilinear relations are indeed nothing else than they can be encoded in the Jacobi identities, or graded Jacobi identities, or certain classes of superalgebras. And then this prompted the fact that you can use representations of Lie superalgebras in the construction of parastatistics. Much more recently, and that is a framework I will use, in 1995, Sean Majid introduced another way to introduce parastatistics, which is useful for applying so-called first quantization. And the way of Majid is to use a Hopf algebra framework, which control, in particular, use a coproduct. The coproduct tells how to construct a multi-particle sector in the theory to symmetrize. That is the idea. And this should be endowed with a braided tensor product, and the braiding should be consistent. This is the scheme of Majid. There is not many papers, but there are some papers working on the relation between the traditional trilinear relations by Green and the Majid approach. So far, so good. Now, question, main point. Soon after the introduction of Green parastatistics, a question arose. Well, where are paraparticles? In nature, we only observe bosons and fermions. So, are there paraparticles? Are there not? Maybe paraparticles cannot be observable. And this prompted some ideas that you can only observe bosons and fermions and not paraparticles, because in a sense paraparticle can always be reconstructed through ordinary bosons and fermions.
In the algebraic context, it is maybe more radical, and even fermions. I mean, fermions are a causal thing, no, that do not commute at spatial distances. So actually, they also cannot really be observed. What you observe are like the consequence of fermions
very good.
Into the bosonic.
Absolutely, very good point. Absolutely, very good point. And you know, well, in low dimension, you can realize fermions as a non-local vertex operator, that's something like that. And similar arguments were put by Araki. You cannot observe paraparticles because there are some Klein operators that can reconstruct. These arguments are bogus. Anyway, you have something more deeper to rule out parastatistics. And something deeper is this conventionality of parastatistics argument. I recommend a beautiful paper by Hans Albertson, is a very well-known philosopher of science, putting various different arguments how to possible rule out the parastatistics. There are several arguments. The most relevant one is, and was also discussed here, the Doppler-Haag-Roberts approach based on the principle of localization. So, if you accept this principle of localization, you can rule out parastatistics. But the question is whether this kind of hypotheses are applied or not, and that is some other point. Okay, so very recently there are 4 papers which proved that paraparticles are theoretically observable. I will list them. I will also explain. So the first 2 papers was the first theoretical test. I will give you the example why was proposed, just to make sure in some control system based on combinatorics, whether you have some test which tells you if there are some observable that cannot be reproduced by ordinary bosons and fermions.
Yes, so it's more than 1 + 1, and also it is continuum or lattice?
I will explain you later. In principle, it can work for any dimension, because the parastatistics based on the permutation group can extrapolate it to any dimension.
So, and the constructions are on the lattice? And the constructions are on the lattice?
There are different kinds of construction. In these 2 papers, the construction is based on the notion of multiparticle quantization, when you have a Hilbert space, and then you can construct a n-particle sector symmetrized in a proper way. We'll see that. 3 years after this, Bang and Hazard produced some systems of spin chain, and one of the systems was related with the kind of structure of parastatistics, the two graded that we'll discuss later. And they have other systems, and they also reach the same conclusions in this kind of contest. The same kind of another analysis, another paper was done with this group of students of CBPF. Rodrigo defended his thesis last month, and I will also discuss about this. All these reach the same conclusion. And all reach tells in which way you can supersede the hypothesis of localization. If you use multiparticle quantization, you don't even have a concept of localization, a la Doppler-Haag-Roberts. If you use the approach of Van Hazard, well, they have some spin chain, and they construct the excited state by using non-localized operator. They're stringy in nature. And in this way, they can overcome the applicability of the localization principle assumed by Doppler, Hagen, and Roberts.
Sorry, can I ask a question?
Yeah.
Just to understand, how do I think of these
Sorry, okay.
These Z2 cross Z2 parabosons? Do you mean like they're anyons of?
No, they're not anyons because anyons,
Z2, no?
anyons are based on the Braided statistics. These are just some representation of the permutation group. But I will show you in the next transparencies how they work. Okay.
Okay.
Besides the theoretical advance, there are also some experimental advances. And one of the first interesting experimental advances was also some 3 years ago. There was a group in the United States by Huerta Alderet and collaborators, and they had some mechanism, they proposed some mechanism to engineer paraparticle in laboratory, and the mechanism is to use some ion trap. They have some different level of energy, and with the laser pulse they can modulate this. So this is the idea, and this kind of paper that they tell that they have all the technology. This paper, however, have not been published, and the reason why they have not been published, and we'll come back later on that, is that because, well, they can engineer this kind, they can use this, but we are not able to prove that the system that produced in this way couldn't be recovered from ordinary bosons and fermions. And I will go back to this point a little bit later. So this is just some setup. And now I will tell you the simplest example, the minimalistic example of paraparticle. And in order to do that, I just make this slide of timeline of superalgebra in particle physics. Everybody knows about the famous Coleman-Mandula-Nogo theorem that tells you in the 60s that basically the role of symmetry is limited because you cannot put in the same multiplet particle of integer or half-integer spin. That was in 67. But in the same time, both mathematicians and physicists, they started working with the concept of superalgebra. And when you have superalgebra, then you have some fermionic operator, anti-commuting, they have some half-integer spin, and voila, you can get all the notion of super Poincaré, algebra, and so on. And just a few years after, Haag, Łopuszański, and Zonius, they classified all possible super Poincaré algebra based on what? On point particle quantum field theory. So you can overcome the Nogo theorem with some sort of Gogo theorem based on superalgebra. And this is not the end of the story, because just 7 years after, Dowry and Frey, they proved that it is possible to go further, to introduce the notion of saturated supersymmetry, when you have the fermionic degrees of freedom, the anti-commutator, and the right-hand side, the bosonic degrees of freedom are the same, not like in this point particle case. And this is applied to what? When you have extended objects like branes. The most celebrated example is the 11-dimension M algebra. There is a side story which is not so much known, and the side story comes in 1978. Rittenberg and Wheeler, they introduced an extension of the ordinary Z2-graded Lie superalgebra. They introduced in the simplest example another Z2, and they proposed this kind of framework. Was later investigated by Schoenert in the mathematical side. And so it was investigated, but not so much as it should have deserved. They proposed the name color algebra because at first they wanted to apply to quarks. Why it was not so much investigated? because the objection based on conventionality of parastatistics. In recent years, in the last 10 years, several groups, our group in Brazil, the group in Japan, in Belgium, in Germany, in Poland, in Australia, and so, they realized from different approach from theory of symmetry of partial differential equations, the appearing in some physical systems that like non-relativistic Levi-Leblond spinors, etc., that this kind of model are there to describe some systems that were even produced before Rittenberg and Wheeler. And then we started all this kind of construction. What does it mean? Systematically, classical mechanics, quantum mechanics, superspace, manifold, etc. Okay. I like to call this construction by Rittenberg and Wheeler the two-bit physics for a simple reason. Okay, I use commutator and anticommutator with curly bracket for anticommutator and regular bracket for commutator. And you know, standard physics, when you have only bosons and fermions, well, it is pretty easy. You can associate the bosons with the 0, fermions with the 1. So just one bit, and you have a table like that. You know that bosons should commute with bosons and fermions, while fermions should anticommute. And the presence of the anticommutator tells that fermions satisfy the Pauli exclusion principle, so you cannot have more than one fermion in the same excited state. Pretty obvious, pretty simple. This is the table of ordinary physics, right? What about Rittenberg-Wheeler Z2, and why I like to call two-bit physics? Because, well, probably you noticed the poster by Gianna on there. So this is the first example of two-bit superalgebra by Rittenberg and Wheeler. And two-bit because instead of having just 0, 1, you can accommodate in two-bit setter the particle this way. And what happens is the following. Besides the bosons, which commute with everything that accommodate in the 0, 0 sector, you have some type of particles, let's call 1, 0 and 0, 1, which are fermionic-like. What does it mean, fermionic-like? It means that they satisfy some Pauli exclusion principle because in the diagonal they anticommute with themselves. On the other hand, these fermionic-like particles, they are parafermions because they commute among different sectors. Okay? And the consistency required to have an extra type of particle, which are parabosons or exotic bosons, because they are bosonic-like. They do not satisfy Pauli exclusion principle because they commute among themselves, but they anticommute with the parafermions. So look at this table. This table is a true generalization of ordinary physics. Why is it so? Because take a bags of particle, put all particle either in the 0, 0 sector or in the 1, 0 sector, and leave the other sector empty. So if you just look at this subsector here, well, you recover the ordinary one-bit physics, ordinary bosons and fermions. But if you have other type of particle, well, you fill some scheme like that, you have something more. So if this is like that, you would assume that this kind of theory would have been investigated properly. And this was not done. Why? Because the assumption, or better the prejudice, that the parastatistics, well, you don't need to work, because in any case, you can always recover them in terms of ordinary bosons and fermions. So that was the idea. I give you, there was not investigating in detail, but since Hermann Verlinde presented on Monday some talk concerning the Sitter gravity, I want just to give you some flash of a very old application. In 1985, don't ask me why, It was 10 years before
So, can we go to the previous slide, please?
Sure.
So, yeah. So, one way to recover the currently known physics in this table is to imagine that there are two types of fermions, the 1-0 type and the 0-1 type, which have an interesting property that the different types would commute instead of anti-commuting.
Exactly.
Why don't we have those? Why don't we have that? Because that would be like a richer way of before incorporating the 1-1 particles, maybe we should first look for fermions that commute instead of anti-commuting.
That's exactly the point. And we will give you the example. I will give you the example.
Okay. Thank you.
But so let me tell you something, because that could be quite interesting, in fact. So I don't know why he was interested in 85, Misha Vassiliev, in de Sitter supergravity, because it was 10 years before it was shown that the universe is accelerating. Anyway, he showed that, the Sitter supersymmetry, the Sitter supergravity has a lot of problems, and some of the problems are solved if instead of using ordinary Z2, you use the Rittenberg-Wheeler Z2, some of the problem. So that could be quite interesting. Okay. Beside this 2-bit physics which contains parafermions, you have also another table which only parabosonic particle, and this is the two consistent extra tables of 2-bit physics introduced by Rittenberg and Wheeler. Okay, well, this is some algebra that have some system of brackets that are just commutator or anti-commutator, satisfy some gradings, and have some generalized graded Jacobi identity. So they are not ordinary Lie algebra and superalgebra. They're something else. And now comes the question. And the important question is the following. Well, if we have this 2-bit color particle, and with that we know that this is an extension of ordinary physics, can we observe their color or not? And a positive answer would prove that the Rittenberg-Wheeler are indeed something to stay there. And this was not just some theoretical question. This was quite interesting because in a brilliant paper, Bruce and Dupley produced a model, this kind of model here, and they showed that this kind of model is admit a Z2 graded one-dimensional Poincare invariance. But this kind of model, this kind of matrix differential operator, is also an example of supersymmetric quantum mechanics, ordinary supersymmetric quantum mechanics of matrix type. So the question, the natural question was the following. Okay, it is nice to have an extra symmetry, Z2 graded or something, but the question is, okay, what is the physics of that? Can we detect physics out of this? And the answer is no. If you just look at this example, you cannot detect any physics, it's just some reformulation of the same theory. On the other hand, however, if you just use this as a single particle Hilbert space, and then you perform the first quantization procedure to construct 2-particle, 3-particle, and multi-particle Hilbert spaces, then you have a possibility to detect the parastatistics. And you can reduce all these problems to some just a combinatorial problems where you have some bunch of signs. And that's, you have to use this kind of framework here, Hopf algebra framework. In Hopf algebra framework, you have a Lie algebra, G. associated to Lie algebra, you have the universal enveloping Lie algebra. You can think of the universal enveloping Lie algebra as an algebra of, let's say, spectrum generating algebra of the theory. Think in the simplest example as an algebra oscillator of this type. And using this kind of framework, you have in particular a concept which is the concept of the coproduct. The coproduct map U into U tensor U, and there exists a notion of co-associativity of the coproduct, which tells you that you can repeat the application more and further, and this delta encode the notion of the symmetrization, or better, the generalized symmetrization for this theory. So that is the idea.
You mean finite dimensional Lie algebra, right? Not finite Lie algebra. You mean finite dimensional Lie algebra, right?
Finite dimensional Lie algebra,
not
yes.
finite.
Or can be finite dimensional Lie algebra, finite dimensional Lie superalgebra.
Yeah.
Or,
it was still infinite.
You can even go not finite dimensional, even Kac-Moody algebra and these sort of things. No problem. Okay. Now, the point is the following. Majid tells how to make to introduce fermions in its framework, and there exists a specific example in chapter 10 of his book, but he doesn't go further. He just says how to make fermions in this kind of system, and the Z2-Z2 grading is the next simplest example. So I just give you the example of how to introduce fermions in Majid, and then you can understand how it works for more complicated cases. Let us suppose that I have a fermionic oscillator. Fermionic oscillator are nilpotent objects, and FF dagger are just the identity. F dagger is creation operator. You can represent these as some matrices like that. That's simple. Now, the coproduct has this kind of property. It maps some Lie algebra realized in the Hilbert space of a single particle into a homomorphism of a Lie algebra realized in the tensor product of two Hilbert spaces. And since you can use U as a spectrum generating algebra, well, basically it tells you that if you have H1 your Hilbert space, you can go from a Hilbert space H2, which is a subset of tensor product of H1, tensor H1, which is induced by delta G, the coproduct of any element of the Lie algebra G. That is the idea. And what happens if F dagger, is a fermionic operator? If F dagger is a fermionic operator, well, you know, when you have fermions anti-commute, and in particular, if you have something like that, identity, when you go from a fermion on the right to the left, you get a minus sign. If you want, you can put a BR, means braided tensor product. This means that you have to put a minus F dagger tensor identity tensor F dagger. This is the Majid framework, which is minus F dagger tensor F dagger. And this is the consistent way to do that, because F dagger squared is 0, because it's a fermion, it's nilpotent. And when you apply the coproduct, this is the coproduct delta F dagger multiplied by delta F dagger. If this is bosonic, should send something of this type which is different from 0. But if you accept this kind of prescription with the minus sign, everything is consistent. And you have the realization of the nilpotent in the two-particle sector. Okay. So once is this, you can do construct the multi-particle sector, and you can apply now to this kind of system like multi-particle sector of Bruce-Dupley matrix oscillator. That's very simple. And then you can check it out what happened. And now, instead of having just one sign, like here, you have a bunch of signs because you have your operators are of this type. And now what you can do is just performing the analysis. You apply all possible creation operator in the two-particle sector, and you check under which way you have some switching of sign. And now what you ask is the following. You ask from some observable. The observable Hermitian operator should belong to the 0,0 sector. Why? Because of what you said. Fermions are not observable. You need to have all observable should be some operator which besides being a Hermitian should have real eigenvalue. So a single fermionic Hermitian operator is not observable, but a bilinear combination of fermions is observable because the eigenvalues are real. If you take some graded object like fermions, you get, instead of making measurement of real object, you have a Grassmann parameter. You don't want that. The same is here. You have this, and you have to find out some operator, and you are able to do that, which tells you what is it. And we can measure whether the same kind of system, in this example for bosons and parabosons, you can map this system of boson parabosons just in some sign, plus or minus 1. And you have this kind of things that basically you have some chirality that differentiate the bosonic state, multiparticle bosonic state from the multiparticle parabosonic state. And the question is whether this is observable or not, whether you can find some observable operator which measure this sign as eigenvalue. And this is the very minimal Gedanken experiment to detect paraparticle. Basically, you can always say, you can find out that if you have your experimental friend that produces a state in this system on the other room, you can just take the measurement, you put this in the same eigenstate of energy, but now you want to have an extra detector to measure if this is a true pair of bosons or parabosons. This means that you have some detector which has some chirality in a yes-no experiment, and the first measurement can tell you that you can use to calibrate this, and the second measurement can tell you if the set of particles that the experimentalist is sending are of the same type or not of the same type. This is the first minimalistic Gedanken experiment. You have some more even bigger framework. Here, for instance, you take superconformal mechanics, quantum mechanics, SL2/1. The superconformal mechanics, you can have introduce, this is the Hamiltonian of superconformal mechanics, but you can also introduce an extra term which is oscillator term. This is known the alpha of Fubini-Furlan damping in such a way because superconformal quantum mechanics doesn't have a proper vacuum, but when you introduce the damping factor, you have a proper vacuum. You can construct all tower of state out of this. The spectrum generating algebra is the same. And then you can get this kind of theory in this particular example. Now you have two sets of creation operator, and then what happens in the possible assignment of this creation operator. This is again for the two-particle second excited state. You can see that you have a bunch of sign coming from statistics or parastatistics for these two type of object. And the question is the following. You have two excited states. In the original case, for super-conformal quantum mechanics, you claim that these are fermionic-like objects, and then you can measure the degeneracy of the second excited state. You have two. If they are bosons or bosons fermions, they are different number. But you can also claim that you modify the statistics in such a way to be parabosons or parafermions, and you have different degeneracy level of this type of here, all coming from this. Okay? So, this is another way to measure parastatistics out of this. Wow. Okay, so now, the point. Can we engineer this paraparticle? In principle, it is possible, but we need to find a midway between experimentalists and theoreticians, because the experimentalist should try to engineer some kind of models that are known on theoretical grounds that cannot be reproduced by ordinary bosons and fermions. And this is a challenge. It has not yet been done experimentally. So it's an open question, which is quite interesting, and it's apparently it's in the reachable of things. Okay. 5 minutes? Yeah, sure.
Until now, everything that you have explained is just 0 plus 1 dimensional.
Not, it can be, it's more than that. Because this theory can be, the problem is the following. The point is you have to prove that this kind of theory are consistent and give some information that cannot be recovered from ordinary theory. That's the point. And once you have that, you can do for all other classes of model, more general. But now I want to go, unfortunately I have, instead of taking my Braided majorana qubits, I take, this was introduced 2 years ago in this paper in nuclear physics. It's a beautiful construction, by the way, very beautiful. And last year they have some truncation at the root of unity because they go in the framework of the braid. And with some very interesting mathematical framework, which was introduced by Lattice and Serganova, but this is not exactly that, and there are some points here. Now I want to just present a very new result with Jeanne, and she pointed out, in fact, that this Rittenberg-Wheeler color framework is not necessarily to go to the n-bit parastatistic where you have only the notion of commutator and anti-commutator, but you can go further. This is taken from a paper by Scheuner. It takes a graded abelian group, and you can introduce the so-called commutant factor, which are in some puncture complex plane. They are defined by epsilon alpha beta. Alpha and beta are grading in abelian group. The simplest example that go further are modular group. And you can introduce some notion of some brackets defined in this way. So, if you take the modular group to be Z2 or Z2, Z2, Z2 n times, you have only commutator and anti-commutator. But the simplest interesting case where you don't have commutator anti-commutator is when you start introducing Z3 grading. This is not enough. This is a modular group Z3. This was used by a lot of people that tried to do, they did ternary physics, like constructing third root operator of, let's say, Klein-Gordon, Dirac, something like that. But this is something which is not, still trivial. The simplest example where you have something non-trivial is from Z3, Z3. When you have Z3, Z3, this is the most general table that you can have here, consistent, with some commutant factor which, in this case, is something like AB is AB minus epsilon BA, depending on this, and epsilon can be, if it is 1, this is just commutator. If it is different from 1, it's something else. And what is this J? J is, by consistency, a third root of unity. And now there is an interesting point, which is the following. This is the table for Z2, Z3, Z3. So, I list my series of polynomials, and I ask you, which are the solution of these guys? Which is the solution of x equal 1? 1. Which is the solution of the equation is square equal 1? 1 and minus 1. Which is the solution of the equation is cube equal 1? 1 e to the 2 pi I over 3 e to the 4 pi I over 3. What is the solution of e square? Is 4 equal 1? 1 minus 1 I minus I. This is a very interesting concept, which is the following. It is the root of unity level. 1 appears here, the first polynomial. This is level 1. Second equation appear for the first time minus 1. This is level 2. Third root of unity. You have 1, but 1 already appeared here. But you have now 2 root of unity which enter here and here. This is level 3. Level 4, you have this guy and this guy which enter. Now, this equation here are satisfy this condition, j cube equal 1, but if you want to have something non-trivial here, you should not put the j equal 1, you should put the j one of these level 3 root of unity. And level 3 root of unity satisfies some condition like 1 plus j squared equals 0. While if you take 1 plus 1 plus 1, this is 3. And the difference are very... So this has a lot of application. Well, I can skip. You can construct oscillator, which satisfies some algebra of creation of mixed bracket of Heisenberg algebra, defined by this guy here, that are not purely commutator, not purely anti-commutator. And if you take a j equal 1, you can have some set of system in two-particle set. You can have, this is here. You take a two-particle set of distinguishable, which depend on x and y. You normalize you put in this eigenstate, you normalize the probability density of finding a particle around x and y. If it is bosonic, you have this kind of shape. If it is anionic, in this particular example, has this kind of shape. Why? Because in one case you have 1 plus 1 equals 3, in the other case you have 1 plus j squared equals 0. And you have another way to measure experimentally this kind of theory. Yeah, okay, so I just want to show you this point here. So if you have creation operator, if they are commutative, you can construct a Pascal triangle. Seriously for fermions, something like that. You have fermions this way. You go from one fermion, F dagger 1, F dagger 2. They anti-commute, so you have 0 here. Everything is 0. If you have two perfermionic oscillator, well, you have something here which is different from 0. What about bosons? If you have ordinary two-particle sector, well, you have the ordinary Pascal triangle, because you can go from here to here in this way or in this way, and this sum, and then you can further, you have, of course, the standard Pascal triangle. But what happens if you have some third root of unity, parabosonic oscillator, which do not commute, as in this case? Well, you have some sort of Pascal-Sierpinski triangle, because when you go from this way, you have this, and you have some 0 that appear related with this fact of this type. And this is something which is also measurable in this theory. And you have some truncation phenomena which exist in this kind of level due to the fact that you have a relation of that. So, I should say that the braided majorana qubits satisfy some parastatistics of Gentile type, where if you have a level 3 root of unity like this one, you have at most 2 excited states, then you have some truncation which come from this. If you have 4 root of unity, level 4, you get further, and then you have a plateau. You can get at most this state. For n equals 5, you can go further, and so and so. You can, each time you can go with the plateau further and further, and in the limit, when n goes to infinity, you don't have a plateau. And that's the braiding of Majorana qubits that you can realize in this way. And this is the mathematical structure. Sorry, I will stop here. Unfortunately, it has some other point that I want to mention, but I don't have time, concerning graded Bolychenko algebra, which is quite interesting mathematical structure, by the way.
During the break, so unless there's a super urgent question, we can postpone that till the break, and we'll reconvene at 4:15. Thank you. So let's thank.
Thank you for the attention.